Tonight we're gonna mess with some simple electronics. And my goal simply is to make a little circuit with this breadboard right here. We can measure it with our multimeter at some point, maybe make it fun, and maybe draw a little circuit and have our elements, measure the voltage going across them and the current going through them. But essentially it's going to be a simple series circuit as opposed to a parallel circuit. But so that right there would be a parallel circuit in which you have a fork in the circuit. Two branches come off the same node, and then they recombine down here at the terminal. But I'm going to do that to show that there's a potential for inserting a lot more elements right there. And we're going to get those out of our bag. It's going to be an LED circuit. All we're going to do is, just like I got here, just make some resistors, some LEDs, plugged into a power supply, a positive and a negative, from this gentleman right here. And let's have some fun with it. If you guys know anything about electronics, this is going to be maybe boring to you, but if you know nothing, maybe you can learn some basic ideas and concepts in electronics. So, first off, we got our needle nose pliers right here. These are just useful because the breadboard, I guess first I'll explain the breadboard briefly and why we use it. It's for quick prototyping, which just means that you're exploring ideas, and instead of having a circuit with soldered parts, it allows for quick placement of parts onto a conductive layer. So let's try to find a circuit board real quick. I think I have one in here. Here we go. Okay, so right here, you can see this is actually an old fan remote, a ceiling fan remote right here. And this is the LED right here. So in essence, it's pretty useful because you can see how it breaks down. Something like a fan remote is quite basic, actually. I used to think it was way more complicated than it is. But all you have is a battery. You hook up your And let's see. So the battery powers the whole circuit. The LED simply acts, it doesn't do anything other than act as an information indicator. Lets you know that when it lights up, this thing has registered your press of the button. And these, hopefully I can explain it right, but this just means, let's see. So these things right here are where the buttons go. And there's actually a thin layer of grease, conductive grease, meaning grease that allows current to pass through it. And let's see, how would it work? When you press the button down, you can see these things naturally by themselves. They are, let's get it right. There we go, I guess that's good. These are broken circuits right here. All these little lines are green coated insulated wires so that when metal touches these, it doesn't make contact with the actual metal underneath. But right here, the buttons press down and the liquid grease makes a contact. It makes a connection across these two. So normally this and this part right here are not connected because you can see they're broken right there. And as you press the button, each one of these makes different parts of the circuit connect with other parts. So that would be high, low, high, medium, low, off, or I think this was the light control, and this was off. And these ones with the stripes, with the bands on them, they are resistors. All they do is limit. It's kind of like putting in a stream. It's like throwing some big boulders to kind of slow down the overall flow of water in that part of the river. The resistors really just add some sort of obstruction to the flow of current. Current always likes to flow in the path of least resistance. So if I took a wire and connected it across, what would likely happen is that the potential across our battery here is what is the driving force. It's a segregation of negative and positive charges, which naturally want to combine together, but the battery itself is designed to not allow that. So you have to connect. You have to let them come together through an alternate route. And that's why it's so useful, because you connect to the terminals of the battery. Instead of flowing together through the battery, they have to flow around the external connection. So if you have a wire connecting here and it's not touched, it doesn't do anything if it's detached from this negative terminal. But as soon as you touch it, the current wants to start flowing. And that's how you can light up LEDs. But if you have the current likes to take the path of least resistance. So instead of flowing around here, if you connect this bare wire with no resistors or capacitors or diodes, the current is going to completely avoid this branch and go down this obstacle-free branch, and then you would quickly have a short out, because the flow would have nothing obstructing it, and it would quickly diminish all the positive charge. They would, as fast as they could, flow through this wire. They would try to reconnect with the negative charges, and likely, very, very likely, this wire would overheat, and possibly that's what a short is. Start a fire. It just heats up so much because you have so much movement of electrons through this wire. So, and very, very briefly, the convention is what direction, when we're talking about current, what direction would current flow? On paper, when we're writing circuits, we always say it flows from positive to negative. That is the direction which, in reality, a positive charge, which is, I'm trying to make this simple. In reality, what's happening is electrons are negative charges. That's just how we set it up. They are the opposite of the positive charge found in the nucleus around which they rotate or exist. Electrons always want to go towards the positive charge. In general, positive charges they repel the electric field. Negative charges attract. They have a field pointing in their direction. And so, if you have a positive and negative charge, they're both going to be doing work to come together. And so it's like you have two sides of the boat rowing in the same direction. So if it helps at all, just think of it like that, where these two always have an affinity for one another, to be close and neutralize each other. That's another way to consider it. And current is considered the direction a positive test charge would flow. So this negative side is where the electrons reside. And when you have a positive or lack of electrons here, there's a field, an electric force, electromotive force it's called, EMF, that's created between them. It's actually written like, I was just thinking, it's actually written like this. One of those fancy E's. And the electrons want to go. They want to move immediately, and there's no space in the wires either. So it's not like a lone electron is being thrown down a hallway and it takes time for him to travel. It's, in fact, the exact opposite. There is, you could think of it as zero space between any of the electrons. So when one moves just a nanometer in this direction, if it is allowed to move, that means all of them have to move. And the stronger the difference of charges between these, then the more charges this force is able to move across the wire. So it's the actual metal wires, it's the actual atoms in the metal wire whose electrons are the thing being moved. And metal is a conductor, which means its properties allow for more easily, for the electrons to be more easily moved versus a piece of glass or plastic. Those are considered insulators, and their electrons are much harder to move for physical and chemical reasons. So this breadboard is an easy way for us to prototype and come up with different combinations of diodes, capacitors, and circuit microchips, resistors, LEDs, which are a special type of diode that has stands for light emitting diode. Just means that it has a chemical compound inside here that reacts in a way that gives off a specific wavelength of light. And this right here, interestingly enough, is allows a specific combination of signals, I suppose, to get processed through this microchip. And so the microchip then knows which wireless signal to give off to communicate to the respective fan it's supposed to control. And that's essentially that. But so I learned this growing up. Me and my brother luckily had 2 fans. We were balling, and we had a fan in each of our separate rooms. And I realized that I can open his up and see that his remote looked like this. And so if I changed mine like this, it stopped controlling my fan and started controlling his. So that was cool. And this circuit is designed for exactly that, that purpose, to work, to control a fan. But instead of having to bust out the soldering gun and make all these solders, which are obviously a struggle to undo, you simply use this breadboard to make connections. You have a little piece like this, and it fits right in there. So that's what we're going to do. These little pieces right here, by the way, are called jumpers, to jump from area to area to make different connections. And this breadboard essentially looks like this. Okay, so these looks like it goes this way, are what are called the rails, or the power rails, I believe, and they are all one connection. So when I plug this red wire in right here, the row that it's a part of, if I plug it in here, every single one of these nodes, here, those are all connected. So this green wire and this resistor right here are also going to get the power that this one has if I connect it. And likewise, this last row right here is separate, but all connected along itself. So this red wire right here and this longer green wire is connected to that. So that's how these two, and then the same for these two right down here. It's alright, it's a little bit sloppy. And then these two areas, you can break these up like that. These are the workspace, essentially. You get the power from your rails. And positive, negative there. In each one of these rows, right here, these numbered rows right here, one is all connected. That's a single strip of metal, you could think of it. 2, 3, 4, 5. Those are 5 separate strips. So all of these 5 holes right here in row 1 are all connected. Doesn't matter where I connect it. And now they are each separate from every other row. So here, for instance, with this circuit here, I grab power from this rail and I connect it to this row, and you can see the LED, it goes through the resistor, slows down a little bit, and the current of the whole circuit is slowed down by the resistor, but it's all moving so fast that we don't consider the current on the front to be moving faster than the current on the back end. It's just all one speed. If we don't have this elementless wire, each of these we call elements, so if we don't have a short wire right there, that's making it easy for the current to go through and skipping this. If all we have is this one circuit, so the current has to go through all these elements, doesn't matter what each of these are, the current up here is going to be the same everywhere along this series circuit. So that's a series circuit, and this is a parallel circuit right here. And here, the current I splits up into I1 and I2. Here, if this was a smaller resistor than this, it's less resistance, so I1 would be more current flow. It would allow more current. It would give less resistance to the current, and so more current would choose the path of least resistance and flow through this node, this branch, and this one would still have some current as long as it made a connection. But if this was bigger, value of ohms, let's say 10,000 ohms, and this was only 1,000, much less current would flow through this branch. So the currents would not be equal in a parallel circuit. But that's how the breadboard's broken up. So that goes down all the way down here, and over here is another separate set of rows. This side is not connected to this side in any way. And with all these separate little connections, we can jump wires from here, from the rail to get power, and then from here to here, and then from here all the way back to complete the circuit. Let's get our diodes out and our little resistors, power up our power supply there, and try to make a simple LED circuit. Okay. So we got a little solar panel which I never opened up. Maybe I'll try to use that one day. Here, just wanted to show you, this is what a computer RAM chip, set of chips, looks like. This is for, you can see it says on here, maybe it says it on the back. Yeah, there we go. So each of these chips are, I think this was a 4 gigabyte chip. So each of these is 500 megabytes, I think. Anyways, you just open it up and slide them right in there. That's what one of the perks of having not having a MacBook. But so far with my Asus, I'm not too happy with it. It's breaking down in so many different ways that the ability to add RAM to it didn't really balance out. Anyways, so here's some diodes. Here's some more little microchips that I never used. Here's a generic LCD screen. Look how clean that looks. So we're gonna leave that on there. Here's a couple more LEDs. And in case we run out, we got plenty of LEDs. Alright, so let's go ahead and put everything away that we don't need. I always like having a clean workspace, relatively. Here's a whole pack of jumper cables. Little baby ones for our breadboard, if we need them. This is a speaker, obviously. And if I really knew what I was doing, I would probably need some of these capacitors. So I might, but I don't know how to just... This is going to be purely an impromptu assembling of a circuit, and we are definitely going to find out whether it works or not. I 100% don't know ahead of time. Okay. Let's put these over there. Organize our workspace a little bit. And, okay. Let's turn on our power supply now. So, this just plugs in to an outlet, and you have two leads like this. And all we're going to do with these is hook up, and we just turn this on. Make sure these aren't touching. And there we go. So we can adjust the voltage and the current right there. leave that in the picture. And here, if I plug the positive here, hook it up, the negative, I complete the circuit, and there we go. You can see the LED turns on. And so what's happening here is we have 3.8 volts going down this whole rail right here, following the red line, flowing from positive to negative. And it doesn't go right there, it goes through this resistor, connects here, and this is the anode, which is the side that attracts the positive charge. Remember this, from positive to negative is the direction which a positive charge would flow. But in theory, it's the negative or electrons, the negative charges, that really flow. It's just the weird convention that physicists decided to use after Benjamin Franklin coined that nomenclature. We could see these two right here connect along this node. So the cathode of the diode is connected to this wire, which is then completing the circuit, connected to the negative power rail, which goes all the way back to here. So in essence, that's it. A diode is unique. It's the technology that comes from the transistor, which I don't know enough to be able to explain completely, but my teacher said that a transistor was one of the most important inventions ever made, because it allowed our current level of technology. In fact, one of these integrated circuits that I pointed to, for instance this guy right here, and this right here is made to be physically soldered by hand. It's really big and has leads. Transistors are so small that modern ones are able to control individual electrons, individual atoms in their electrons. This diode is one of the products of William Shockley discovering a weird property of semiconductor material. You remember I said before that all these are made up of different bits of conducting metal, and all these wires are metal. Obviously these are metal. Current flows very easily through metal. It doesn't flow through plastic, this whole thing right here. Semiconductors are a weird mixture of mostly silicon, which is sand, essentially, melted down sand, with precisely measured and added impurities. So you have silicon, a pure element, with bits of impurities of other elements in it. So for every 1,000 elements of silicon, you have one or two other elements in there. And that little mixture of different atoms with their own unique properties allows electricity to do a weird thing. They're called semiconductors because they neither act completely like a conductor, allowing electrons to flow freely, easily through them when a voltage is applied, but they also don't act like pure insulators. In fact, their properties change when you add different amounts of electricity, or even sometimes, depending on how they are manufactured and designed and created. They react to heat and light even, and that's how photoresistors work. So this diode, interestingly, if I keep this in frame, you can still see the light. You can see it increase as I increase the voltage to 10, 12, 14, 20. And as I go down, it also decreases. When I do this, when I increase the voltage ever so slightly, let's do the current. This thing, it doesn't gradually turn on. It actually abruptly turns on. There we go. And what's happening is that right at a certain voltage, the semiconductor material creates a cascade effect where it acts like an insulator below a certain voltage, which I think is about 1.7 volts. And then after that voltage is hit, it is designed to all of a sudden, like a dam retracting, allow a flow of electrons. So it acts like a dam and stops current from flowing. That's why it's not lit all the way up until 1.7 volts. And then as soon as that, let me turn this down. Let's see. Anyways, as soon as that 1.7's hit, the properties, the special properties of the silicon interacting with the impurities allows a sudden tipping point, inflection point, I guess. That's a new buzzword I'm hearing around a lot. It's a point at which the properties shift and new properties emerge. And so it allows current flow, and then the current interacts with some special chemicals that exist within this device. And those chemicals react with the current to give off red light. So, anyways, transistors are not exactly diodes, but they are made from semiconductor material. And transistors, I've been editing a lot, so I don't know whether I said it or not, but my professor said that in 1,000 years, transistors will be the most important, significant technological invention, and that's because, well, we've been able, great scientists and inventors have been able to stick literally billions of them on an integrated circuit this small. So that's what our phones, all modern, small, sleek looking electronics, they all are only able to be so small because we are able to have transistors fit on a single microchip, so small that they're only 19-20 atoms thick. And yeah, it's really compelling that we've made them so small that they can move single atoms around. And transistors act as either switches, which are on or off, and if you have billions of them, you can create patterns with the on-offs that can be manipulated in the form of binary functions, I suppose, to store data. So you have strings of transistors that can be probed to see whether they're on or off, whether they allow current or whether they stop current, like that. doing that, we can have a map of memories in our computers. And so if you have 16 of those in a row, you have a hexadecimal value represented maybe by the number 9 or the letter A. And if you have 4 of those sets of 16 in a row of on and off transistors, then you have what's called a nibble in computer language lingo. And 8 of those instead of 4, another 4 together with the other 4 making 8, you have 128 bits. Anyways, that's called a word. And modern computers, so that's 128 transistors storing either 1 or 0 on or off values. That's 128 bits of memory right there. And now we don't have millions or billions, we have trillions of transistors making up memories in modern computers, which is really, really mind-blowing to think about. So, anyways, we're going to briefly analyze this circuit, measure the current and voltage going through it. Alright, so we have 5 volts going through this right now. That means that we have a circuit that looks like this. We have our resistor, we have our diode, and this resistor is, we have a way of identifying what the resistor's value is, and man, hopefully we can see it. So right here we have a brown, black, red, and gold band around the resistor. And the box that it comes in, it's a little beat up, allows you to identify it. So brown, black, and red. So brown is 1, black is 0, and red actually doesn't represent the third band, it's the multiplier. You just kind of have to know that, I guess. So X out that, so it's 1 and 0, and then red is times 100. So that means 1,000. 10 times 100. So that means that this resistor is 1,000 ohms. And then our diode here is it's just a red LED. I don't really know if there's any, I guess I'd have to look it up to see the characteristics, but we know that this is limiting the current, and there's some basic equations that you can use to figure out how much current is going across this. And generally, circuits as simple as this are very easy to analyze. When they're in series, again, there's not a fork, so that would be parallel. There's no fork, so it's a series current. That means that the current throughout the whole thing is going to be the same. And current is just current in amperes, is simply, let's put this over here. Current in amps is simply the amount of charges Q in, I always get that wrong. I think the U might be over here, but whatever. Coulombs per unit time, seconds. So it's the amount of charge passing over a given area in a given time. And like any simple system, we can model it with a math equation in the law called Ohm's law, whom the unit of resistance is named after. It goes like this. Right over here. The amount of volts is equal, or is in relation to the current times the resistance. And I remember that as the Spanish word vir. It doesn't really matter what it means, I just remember learning that verb in Spanish. But, and you can mathematically manipulate this. You can also divide both sides by R, and write that the current is the volts divided by the resistance. So we know this value, we just determined it by looking at the bands, and we know there's 5 volts being supplied. So we can figure out the current by using this. So that's just 5 divided by 1,000, which equals 5 1,000ths. So an easy way to remember this, 5 1,000ths. So 5 times 10 to the 3, a 5 would normally have the decimal place here, 10 to the negative 3, sorry. So 5 times 10 to the negative 3, which anybody going in a STEM field, science, technology, engineering, and math, is going to have to learn that. 1, 2, 3. That's 5 thousandths of an amp, or 5.0 milliamps. So that's the current that's going through here. And let's see. Now, the current is always the same, but one thing you'll learn when doing circuit analysis, if you do, is that voltage is considered, it's like almost like potential gravity, where if you have a cliff and you're 20 meters high, up here, if you have a little guy with a really long right arm, I guess, and he drops a ball, that ball is going to pick up speed, acceleration, and by the time it hits the ocean there, it'll be going really fast. But once it does hit a ground, it'll no longer have any potential energy, gravitational potential energy. And so we say that it started with 20 meters of gravitational potential energy, and ends with 0. And we kind of look at circuits like that. So we think of it as losing voltage as it passes over obstacles that resist it, and it ends up at 0 volts. So really we think of it like there's 5 volts here, and there's 0 volts there. It's really just an analogy, but it's a really useful one for solving these circuits. So, let's see. So if I put a big enough resistor right here, essentially, the bigger the resistance, maybe if I make it 1 instead of 1,000, 1 million ohms, and there I do have that, it takes a lot more voltage to push the current through this resistance. And so there's a big voltage drop. And that might be enough, in other words, to drop the voltage, to not create the cascade effect for the diode to change its property and allow the current to pass. Remember, it needs at least greater than or equal to 1.7 volts to operate, to be able to put out light. If this diode didn't exist, and you just have one resistor resisting the current from a 5 volt battery, this would be the current right here. But this LED is has its, again, unique properties. A resistor really acts in a linear manner. It resists and kind of defines what current will pass through. If the voltage is kept constant and the resistor changes in value, the current changes in a very linear, very simple proportion to the resistance. The larger the resistance, the smaller the current. The smaller resistance, the larger the current, if the voltage is kept constant. But this LED, pretty much, again, I said, unless it's greater or equal to 1.7 volts being supplied, the LED acts like a infinite ohm resistor. It doesn't let current pass. The larger the resistance, the smaller current passes. It's like you're tightening a hole through which current or water can flow, to use that often used analogy. But then once it hits that threshold, the LED lets nearly as much, well, it lets a lot of current go through. Its hypothetical resistance drops close to 0. But let's measure this and find out whether that's true. I think I read that there's like a 10 to 15 ohm resistance when the LED is on. So let's find out. Let's, of course, like all realities, the real world is not as perfect as our equations would have us believe, but hopefully it's close. Let's measure it indirectly using the volts. So we have to reconnect this real quick. Okay, oh no, wrong one. There we go. That's the beauty of working with LEDs. At least you know when you made the circuit complete. Otherwise, it's really frustrating. Alright, so at 5 volts, we have a voltage drop of 2.05 volts across here. Guess that's make some room in here. Alright, so we have 5 volts going through it. And if I measure the volt drop, 2.05 across the resistor, so we have 2.05 volts there across the LED. 2.92. Then we can say that if we measure the current going through here, it should be the same because that's how circuits work. So we know the volts, the current going through here, and we can figure out the resistance of this LED. So we do here, we do the current, remember, equals V divided by R. So we have 2.05 volts divided by 1,000 ohms equals, so that's clearly 2.05 milliamps, and so that has to be the current going through the whole thing now. So that means that this diode also has 2.5 milliamps, so we got 2.05 milliamps, and we have a voltage across this I've measured of 2.9, let's say 2.92, something like that, and then we have the resistance in ohms. So if we manipulate this, we're going to get the resistance equals 2.92 divided by 2.05 times 10 to the 3. Alright, so that means that the resistance should be 2.92 divided by 0.00205, and that equals divided by 0.00205, that equals 1424. Really? 1420. That does not seem likely, but so when I looked up what LED's properties are, they, instead of, they're kind of like a resistor in the sense that a resistor is defined by its resistance. LEDs are typically defined by the voltage drop across them, and then they let however much current needs to go through in order to maintain that voltage. And of course that's not perfect, but if this is at 5 and we measured it to be the voltage drop across it 2.92. Now if we increase this, we notice the LED getting brighter to let's do increments. We'll do 7.5. Now it's at 3.05. Not a significant jump. But the resistor is now at 4.3, which, sorry, where was I? Compared to 2.05 like it was before. That's twice as much. And so we bring it up to like 10-ish now. 10.01. The voltage across moved up a little bit, 3.15. And now the drop across the resistor went up to 7 volts. It was originally 2, then 4, and now 7. If we go crazy and pretty much try to blow this diode, light emitting diode, let's go up to 20. See what it is. And it's only at 3.38. The resistor is at 16.3. See if it's getting hot. I don't feel like getting hot, so that's good. Yeah, let's max it out. Let's see if we can blow this thing. 28.2 volts. I can see over here. Now, the diode is carrying 3.5. And I bet the resistor would be up. Well, it's the difference. So it should be around 25 volts of a drop. 24.6. Okay. So what that tells us is that in the current going through this, that's why it's getting brighter, because there's more current going through it to account for the essentially the diode won't change its voltage drop. This resistor definitely will. It has a fairly constant resistance. Let's see, 1000 28, let's just say 25 volts divided by 1000 ohms is, like we figured out, easy math, 25 thousandths of an amp, or 25 milliamps going through it. And so that's what's going to be going through this. So it increased by about 12 times what it originally was. But this diode, I believe it doesn't quite obey Ohm's law, so we can't really find out what resistance it has due to that. So anyways, that's a little interesting thing, is that this has a constant resistance and this has a constant voltage drop over it. So I guess we'll call that a lesson for today. If anything, we learned how to hook up a very, very simple circuit, and that was plugging your leads, positive, negative, hooking your resistor up to it, and then downstream from that, and then connecting the cathode end of the LED to the negative terminal right there. So this was kind of fun, slightly frustrating at one point, but it's alright. We did some math, we figured it out, we had some fun. Got to bust out my old electronics equipment. So I hope you guys liked it. Let me know what you thought. I really do value your feedback. It's really important to me. It really helps me know what you guys are interested in, and where I should take the channel. So I'll see you next time, guys. Till then, please sleep well. Have a great night. Bye.